Hello everybody and welcome to session number 20 of my lecture on statistical energy analysis and hybrid methods. This session will be about the coupling of systems, and you will learn how a deterministic system called FEM system is coupled to an SEA system and what is the impact of the SEA system on the FE system. If we do so, we create a very straightforward approach to the global theory of statistical energy analysis. And on top of that, we have a very easy and simple and clear formulation of how coupling loss factors are calculated. Good, so let's go into the details. Before we get to the details of random systems, we have to talk about how finite element systems are dealt with in practical details. Normally, if you have a huge mesh, you might have a million degrees of freedom. And the easiest way to handle this is that you arrange things a little bit. And this is done by checking out of what kind of nodes or degrees of freedom do I have. I have some outer degrees of freedom, which are the boundary, which can interact with other systems. And we have some inner degrees of freedom, which are somewhere in the mesh of our finite element system, but we never have a chance to excite them or to connect them to anything other, to any other points. This is why we definitely know that the external excitation must be zero for those specific nodes. We can rearrange our dynamic stiffness matrix in such a way that we will sort them for inner and outer degrees of freedom. Then we get 4 block matrices: the clear inner or outer block matrix and the coupling matrices between them. So due to the fact that there is no external excitation applied to this upper block matrix, the upper line can be inverted. And that means that we can get an expression for the inner degrees of freedom, which is a combination of this inverted inner stiffness matrix and the matrix of the off-diagonal matrix. If we then finally rearrange everything and use the lower part of the matrix, we can find a new formulation of this. So we have this combination of block matrices, but the good thing is that at the end of the day, we only formulated this in terms of outer degrees of freedom. So all the hidden interiors are now hidden in this outer stiffness matrix. And this is what we call condensation. This is a method that is used also in commercial packages, and then it's called super element. But this is also a method that is used, for instance, if you're modeling trim packages. So some noise control treatment. Also in this case, you model the trim package and just condense all the full trim package on an outer degree of freedom matrix. Good. So far for the arrangement of my, let's say, deterministic matrix. Keeping this in mind, we think about now a system. What happens if we put such a deterministic system, which is represented by a stiffness matrix with the index 3, and we connect it to some, let's say, to 2 free field radiation stiffnesses. So we have a free field here. It could be an open space and half space of air, and we have this on both sides. Again, due to the condensation tricks, we are just dealing with this matrix in terms of the junction degrees of freedom. Talking about junction, the degrees of freedom that are connecting system 1 and 3 or 2 and 3, they are denoted by this index J13 and J23. And we can again form a kind of block matrix here. So our block matrix is just describing these junction degrees of freedom, or the other are just denoting the relationship between both. These are the off-diagonal block matrices. And when we add the stiffness matrices of the radiation field, we just have only the upper block matrix here for this part, and we have the second block matrix here for the right-hand side. When we keep in mind that the degrees of freedom have to be, let's say, distributed in the right way, so that only those parts are added which belong to the same degree of freedom, we can omit this indexing. But we always have to keep in mind that the clear relationship to the degree of freedom has to be considered. And we can write this matrix in such a way. We call it the total stiffness matrix because this is the stiffness matrix of some deterministic system embedded in some free field radiation. A practical implementation of this would be that you take some sheet of metal and put it in the fluid, in air or in water. This would represent the same configuration as you can see it here. So in the very general form, we define the total stiffness matrix as the stiffness matrix of our whatever deterministic system, and we just sum over all radiation and radiation stiffnesses that are connected to this subsystem. Okay, so far for the deterministic part. Now the question is, what is happening if we are coupling random systems? And here the situation is slightly different. So let's have a deeper look into this. Just imagine that we have some deterministic system and we have an SEA subsystem which is random and they are connected. The question is now, how can this SEA subsystem be modeled? And we have learned from all the considerations before that if we have a random subsystem here, in the ensemble average, the stiffness that describes the connecting points here denoted by the stiffness matrix J1, can be represented by the free field radiation stiffness. So that means the impact of this SEA subsystem on this FE subsystem is just given by the direct field radiation stiffness, because that is what is the remaining part if we do an ensemble average. That means if we ensemble average a complete system, so a stiffness matrix with two connected SEA subsystems, we would get exactly the formulation from the last slide. That will be the stiffness matrix of the deterministic system plus the two direct field radiation stiffness matrices. This is the total matrix. So in short, an FE subsystem connected to many SEA subsystems is like an FE subsystem connected to several free field matrices. Good. So now the other story is we know that in our random field we have a loading. So this creates a loading on our FE subsystem, and this is given by a cross-spectral density matrix. And normally it's quite hard to calculate this, but as we have learned, there's an extremely practical relationship which is called the diffuse field reciprocity, derived by Langley and Shorter. And this provides the cross-spectral density matrices from few quantities. It is given by the energy, the modal density, and the imaginary of the free field radiation stiffness, or the real part of the impedance. So that means this is the first hint to our, let's say, how do we do statistical energy analysis, because we have an expression that creates the loading just from the energy and the radiation into this field. Just one remark regarding this imaginary part. This is all true if we're talking about real based coordinates. If they are complex, this is something I learned from the line junctions, the formula here is slightly different, but in general it is valid with this, with a slight modification that I will explain later in a session after this lecture. Good. So far for that. So now we have everything learned. What is the impact of the SEA subsystem on the FE, and we have now understood what is the loading of the SEA subsystem on the finite or deterministic random system. What can we use that for? Just imagine a typical SEA configuration. We have an energy in one subsystem which is stored in the reverberant field. We have something that connects this field, and then we have a transfer of energy from this subsystem N into into a subsystem N. And this is what we have if we would like to calculate the coupling loss factor. So we know that this constitutes a random load which have to be described by a cross-spectral density matrix. And we know that the response of a system to a random load is given by this double triple matrix multiplication. From our derivation of the statistical excitation of, let's say, matrix described system, we know that this is normally done by the transfer matrix H, which is here now replaced by the inverse of the total stiffness matrix. And because this is how we can describe the dynamics of the system here in the middle. So this is the, let's say, the random mechanical response equation. So now we start with this term here. How do we get this? As mentioned several times, this is a stochastic load, it's a Hermitian matrix, and we have all the information we need because it's a diffuse field. And from this, we can apply again the diffuse field reciprocity relationship. So that means from the energy, the modal density, and the direct field stiffness into this subsystem, we can derive the motion of the degrees of freedom that are maybe radiating into the other subsystem. Good. So this is the cross-spectral density response of this junction connected to the M and the nth subsystem. This is the first step in our global hybrid and coupling loss consideration. The next step is, how do we get the radiated power? We know that's quite easy. The radiated power is the imaginary of the product of the forces times the displacement, complex displacement. And we have to sum up our all nodes. So this is why we're just summing up all those single forces. And we have to average over this in an ensemble. We can derive the reaction forces by the direct field radiation stiffness. So we replace the force here by this expression, but now we have to sum over another index, which is denoted here by J. If we, let's say, take the ensemble average of this, we can factor out everything which is not, which is stable in terms of an ensemble. That's definitely the direct field radiation stiffness. We just keep the ensemble average for over the degrees of freedom. From this, we can then definitely calculate the input power in the ensemble average. And this is the imaginary over whole this expression, just summing up over I and J. When we keep in mind that this is a Hermitian matrix, and then we assume what can be mainly assumed, or we take this as consideration, that this is a symmetric matrix, the stiffness matrix can also be factored out. So we have the remaining quantity that is describing the radiated power. So now, if you remember the last slide, this is what we get from the response to our random field excitation, and this is the power output. So that means we have now everything on board to calculate the power which flows from M to subsystem M to subsystem N. And we have the energy here, we have all other quantities, and we have a quite complex expression, which is a combination of total stiffness and several radiation stiffnesses. Perfect, because from this, we have everything that we need to calculate the coupling loss factor. Why is that so? Just keep in mind what is the global form of a coupling loss factor. It defines the power flow from M to N based on the energy in subsystem number N. This is the coupling loss factors, multiplied by angular frequency omega. And that means, with the formula from above, all we need to calculate the coupling loss factor is the free field radiation stiffness of all connected subsystems, the modal density of the source subsystem, in this case M, and the dynamic stiffness matrix of the deterministic component of the junction, if there is any. That means, from the back formula, that this is the global formulation of a coupling loss factor. Excellent, because this is a global formulation that is valid for all kind of couplings in an SEA subsystem, making it extremely useful and straightforward. Good. When I sum up this system over all subsystems, so I'm just considering what is the power input that I get from all my surrounding subsystem, we can write it down in this way, plus the external power that I get from external power input into my subsystem. Just one final remark, if there is no connection subsystem in the middle or whatsoever, the total matrix just consists of the free field radiation stiffnesses, and the structural matrix or deterministic is just missing. But however, it just changes slightly the total matrix, but in global it's still valid. Good. So that's that was the description of all the power that was flowing from M to N. Now let's have a look at the energy that leaves the nth subsystem. So we have some reverberant field which with energy En, and this is exciting here our connected structure. And this is again also mentioned when I'm talking about this is not the dissipation to some damping or whatever. So this is the dissipation or loss of energy that just comes from the connection to this system number En. And the formula is the same as before, but one very important thing, the stiffness matrix that is used now to take the power leaving here is no longer a radiation stiffness, but it is the total stiffness of this inner structure connected to all of the others. And if I, let's say, formulate all the rest, so I take again this expression which is coming from the which is replaced by the diffuse field reciprocity plus the consideration of the last chapter, we can write it in this way. But keep in mind, this is the total stiffness matrix for the coupling loss factor. This is also radiation stiffness, and here it's another matrix. However, this matrix can be let's say formulated again in the original version, taking the stiffness matrix of the inner system plus all the connected radiation stiffness that are constituting this final stiffness matrix, total stiffness matrix. Good. Rearranging things a little bit and sorting out for the other points, we have quite an interesting result of this. So first of all, we have here the stiffness part, which is the former version, plus a term that is exactly the same as before, because that's nothing else than the coupling loss factor from the last slides. And if we reformulate that, that means that the power that is leaving this subsystem is all the coupling loss factors which describe the leaving of the subsystem, like in our classical SEA matrix, plus an extra term, which is this one. And this extra term is the loss is related to the losses into the connected junctions. And this is something very good and new, because in classical SEA, the junction cannot, let's say, consume energy. And here in the clear formulation, we have a loss term of all those energy that is, let's say, dissipated in the junction itself. Good. So as mentioned, this is the additional factor eta and n alpha, and this is again mentioned that this is connected to the losses in the deterministic systems. And this is clear, it's the imaginary part of the stiffness matrix of our system. And this is exactly where the loss and the imaginary part is describing the losses, because the real part is just describing the classical mechanics, more or less. Good. However, this dissipation in the major field is still there. So if there's some wave dissipation, it will be there. That's what we call the classical loss factor. And we can then sum up all the energy that is leaving the end subsystem. So this is a classical dissipation plus the formulas that we have derived before. So the dissipation in the connected FE subsystem plus the power flow to all the other surrounding subsystems that we have. Good. So in the future, we will not, let's say, add this in addition, we just put those together. So that means when we talk about eta and n alpha, it's a combination of dissipation in the junction plus what is dissipated in the field. So now let's go for the global balance of everything, lots of power input and output, and let's assemble the SEA matrix for a second time from the hybrid theory, more or less. What kind of power flow do we have? We have the input power, which comes from the external, could be whatever, an extra force, whatever, introducing energy into our direct field. We have the power input from all the surrounding subsystems. given by the coupling loss factors. We have the power loss into all the other surrounding subsystems given by the expression before. And we have the dissipation in the field, which is from wave field or some, let's say, random boundary absorption. If we set up the power balance of all of this and putting all the sums together, which I will definitely not do in this lecture, but you can do this as a small exercise if you want, you will get a matrix equation which looks exactly like the SEA matrix that I have derived in a more, let's say, general way of balancing the power flow. This is exactly the same matrix. So this is the losses in one subsystem and the power flow into all the other subsystem. And this here is the backflow. So this is the energy that comes back from all other connected subsystems. And this is the SEA equation derived in a, let's say, hybrid way. The only difference is the well often mentioned, let's say, loss factor that includes also the loss in the connected deterministic subsystems. Good. So far for that. Thank you very much for your attention. The next lecture will be about the global procedure in a hybrid method, where we use all the things that we have derived before. Again, if you would like to look much more into the details of this derivation, you will find everything in my book of Statistical Energy Analysis and Hybrid Methods. I hope you had some fun at least, even though this was, again, heavy theory stuff. And next time, as mentioned, the hybrid theory will be explained in a more practical and more principled way. See you later and bye-bye.